So today we have the talk about what's that CubeSat Satellite stuff anyhow by Wouter. So please give him a very warm applause and let's listen to his talk.
Thank you everyone for showing up. Let's start with a round of hands. Who already knows what a CubeSat is? Okay, that's about half, I would say. I'm not only going to focus on CubeSats, but some general concepts for satellites as well. During this talk, there's a lot of slides to go through. There's a lot of eye candy as well. I've brought a few things that I'm going to show. But first, a bit about me. I worked on the Delphi C3 satellite project that is done by Delft University of Technology. It's the first Dutch nanosatellite and first Dutch CubeSat. And then an RF engineer. And then I became more into the IT side of things. If the feedback, by the way, is a problem, I can switch to the stick mic if that's easier for Avi. I hear quite a lot of hum. Yes. So, oh yeah, I can still hear. Can you still hear me in the audience? Yes. Okay. So I am also a radio amateur. Amateur radio call sign. We usually spell them out: Papa Alpha 3 Whiskey Echo Golf. So that's always interesting when people read that and they go, "What is that? Pa 3 weg, PA 3 whatever." Yeah. So that's amateur radio. I own a spacecraft with a non-profit that I'm the chairman of, MSAT-NL. I also do sound engineering, videography, all kinds of electronics things. And I am also in the Angry Nerds podcast in the Dutch language, who also has a village/media village on site. Started with electronics and general nerdery quite early on. Got my first toolbox as a birthday present when I was a child. Oh, and yeah, I'm also in the production house, so all the people that are struggling in the back with the sound, that's also my team, so thanks guys. The contents of the presentation. First, I will briefly go into what is a satellite and what makes space special. Then why CubeSats specifically exist, and then some typical applications. For the space nerds here, I'm going to oversimplify because I can't really fit everything into a presentation otherwise. This is not a corporate talk. I work for a company called Easy Space, and I've experience with multiple head syndrome, and in space you also need to make everything an acronym, so it's now MHS. Which basically means I do this on the side. I also do this as a hobby, but I professionally build satellites as well. And I just asked some of my colleagues, can I have a few of your slides, pictures, etc. Space delivers small satellites and complete missions since we started. In 2006, we have all the facilities to build these satellites in-house. With a lot of people around, with certainly a lot of different nationalities. And we have quite some statistics, 3,000 plus items that we've delivered, 760 satellites that we've helped put in orbit and counting. And we are often on the background, so you didn't hear about us, because there are other people that needs to shine and have a mission, and they take the spotlight, and that's okay with us. So, what's a satellite in the first place? Anything that orbits another body, so an astronomical body orbiting something else. So the sun going, or the Earth going around the sun, we are a satellite of the sun. The moon going around the Earth, that means the moon is a satellite of the Earth. But we can also have artificial satellites, stuff that we build that goes around something else. And that's what we typically call a satellite. So not a lot of people would say, oh, the moon is a satellite, but it is. So in this talk, I will use the acronym or the name satellite as a synonym for spacecraft. So what's so special about space? It's not exactly rocket science, or is it? Space projects are a bit different. When you have a regular project, especially if it's a hacky project, you build and you try stuff and then you fail and you fix stuff and then et cetera, but it will never become factory work. For satellites, all of them are a bit special. There's never, well, with a few exceptions now with Starlink, but it's mostly not factory work. But the kicker is, of course, you can't really call a breakdown surface. It's not like you can have stuff fixed when it's already in orbit. With a few exceptions, the Hubble Space Telescope was fixed by going there with the space shuttle and actually fixing it. That's very rare, so you can't really fix stuff once it's up there. So you need to test it before. I think most of us actually know the Apollo 13 quote.
We gotta find a way to make this fit into the hole for this, using nothing but that.
So yeah, there's an issue. We know what we have in materials, we need to fix it. Humans are extremely good at this, and computers are usually not. Well, in other ways they are with exhaustive testing, etc. But humans are very creative. That's why sometimes you need humans. We don't want to cut it this close, though. This Apollo 13 thing is a story of heroes, but we don't want that. We just want everything to be boring, nice, and stable. And we want to prevent issues from happening in the first place. So we end up testing.
We gotta find a way
Wants to
make this
play again. Okay.
fit into the hole for this, using nothing but that.
Yeah, so we test, and test again. Functional testing is just the hardware and software testing. Then there's environmental testing. You want to make sure the thermal is okay, so it can get hot and it can get cold. There's vacuum in space, so you want to do a vacuum test. Radiation, that's not always done, but there's a lot of radiation in space that you need to check for. Vibration, shocks. Vibration and shocks is actually the launch. That's a rather violent affair, lighting a big candle and making stuff go up to space. That's the violent part. Once it's in space, it's actually peace and quiet. So that's just the few minutes that you need for launch. And then there's all kinds of other testing. End-to-end, does everything work from A to Z, Z? And fault-free analysis, what happens if? And that's a lot of work. And it can also go wrong. For instance, if you have a spacecraft sitting somewhere and somebody borrows the bolts. And then you try to tilt the spacecraft over, because that's what that thing is, the white thing is meant for. But yeah, it wasn't bolted down, sorry. So yeah, that's ground handling and logistics. Seems boring, is very important. Gravity, we have gravity here, and in space we don't, so it's really difficult to test stuff properly. You can go on a parabolic flight with an airplane and then have very briefly some zero gravity experience. Gravity is still there, but you're just falling with the plane with gravity, so it looks like you're weightless. And you need to keep everything very clean, because you really don't want to find out after the fact that something broke because there's a fingerprint on the sensor or something. You turn on your, I don't know, your star camera, and then all of a sudden it's like, ooh, there's a speck of dust over there. And mistakes, obviously, are made. And you need to be prepared to deal with all of those things. Getting there in one piece. This is also one of those things where the launch is the violent bit, and after that you're probably fine. It's a few minutes of very intense vibration, but also acoustics, shock, that kind of stuff. So you can do vibration dampening, you can make stuff shock-proof, you need to test stuff. Acoustic loading, so just the sheer amount of noise from a rocket can really change material properties, make things break. And then cleanliness again. So you do a vibe test, and this can also be rather violent. So I have an example here where we're shaking a satellite in one axis, and you increasingly ramp up the amount of vibration. So there's this little box, and that's housing a very small satellite. I brought I always say a model, but it's a 1-to-1. So this is the size of the satellite. And that's in that little box. And if we shake that, you will see that it will start ramping up and then go really violent. So here it's ramping up in frequency. You can also hear it from the sound. And it's just rattling, and now we start actually giving shocks. And then we're done. And you do that for every axis. And each time you do that, you also afterwards check, does everything still work? Are all the bolts still in? One other thing is radiation. So if you're out there in space, there's no protection from the Earth's atmosphere. So you get the full blast of whatever the sun produces and other stars. So you have to check what materials you use. Can they stand that? There's also a lot of UV light that's wearing down plastics, for instance. You build in redundancy. What if a computer fails because it just receives too much radiation? You can shield from that radiation. That's very difficult in practice. And fault detection and recovery. So something went wrong, we see that something went wrong, and then we recover from it. And it's not as bad as many people think, because these satellites are typically short missions in low Earth orbit, and they don't get as much radiation as a lot of people think. Then the vacuum. Again, material use, specific materials that can withstand the vacuum. For instance, if you know what an electrolytic capacitor is, it has a little cross, usually where it blows up in a nice manner. It actually ends up blowing up from the vacuum, so then your capacitor is instantly useless once it goes into vacuum. So you need to not use electrolytics, or have specific ones that are properly sealed. Heat transfer, there's no air, so we can't have a cooling fan. We need to conduct everything or radiate everything away. But yeah, no fans, that kind of stuff. Lubrication is very difficult, because if you put a drop of oil somewhere, it will basically just vaporize and disappear. Well, not all lubricants, but that's a problem. And component placements, where do you put stuff? And also, if you seal something, make sure that there's a hole so that the air can go out once you launch, because on Earth there's air inside something and it needs to go out, otherwise it explodes again. Then we have the temperature differences. If you go in the darkness, you can rapidly cool off a spacecraft, and then when it comes back in the sun, it can also rapidly heat up again, which is a problem. So you need to take into account expansion, contraction, how to get rid of heat again, that kind of stuff. With gaskets and interface materials, you can conduct heat away more efficiently. A lot of people that are in electronics know the silicone pads that you can put between a transistor and a heatsink. Those things cannot stand vacuum. So you will need to find something else or design your design differently. So maybe for a thermal reason, you have to change your electrical design just because you can't use this material. Or there's other solutions. Then fatigue from just the expansion and contraction. Again, lubrication. Also, temperature range of your lubricants needs to be really high. So that's some of the challenges. And now I'll briefly go into what's that bad about it. Is it really that bad? The FunCube-1 satellites, of which the model that I held up earlier is a prototype, so it's this size. This one sees in orbit the outside surfaces become -22 on the cold side and +31 on the hot side. That's actually not that bad. The internal surfaces are even better, so that is not a huge problem. Then we have another satellite, a relay satellite that is far away, so not in low Earth orbit, but behind the moon from our perspective. And then the outside surfaces all of a sudden go from -90 to +120 degrees centigrade. And the internal surfaces are still kept at -10 to +45, which is a really cool thing to do if you manage to get that thermal design properly done. And then you have to test that in thermal vacuum. This is me in the UK at RAL Space, where they have a big chamber where you can put this tiny satellite in, which they laughed about because it's not meant to be for that kind of small satellite. So there was plenty of space. Put the satellite in there, do some vacuum tests, and have it tested. Then the other thing, I called it the elephant out of this world, space junk. There is a lot of stuff there. Not all made by us, but the majority, yes. All these specs are either satellites or things that we're tracking. Stuff that's out there that we're keeping an eye on. So we check with radars what's there, and every dot is actually either a spacecraft or some old junk. So yeah, there's a lot, but it's also called space. So there's also a lot of space. So luckily, not often something goes wrong. CubeSats are smaller, so they are easier to burn up in the atmosphere, preferably not on the way up. Saving fuel and materials compared to the bigger satellites. So a CubeSat is basically a smaller version of a satellite platform. And yet by making them smaller, you're getting the savings from that. Rapid development is possible, so you can build these things relatively quickly because they're not these really complicated big things. And looking up makes us aware of what's down, so space is still very important because by launching stuff and looking at our planet, we can also see what's happening here and see the big picture. So yeah, don't build in space what you can build on Earth. You don't want to actually launch a spacecraft for something that you can easily achieve without one. We shouldn't pollute space unnecessarily, so don't put up useless junk. The resources are finite, and be a good space citizen. That's for space junk, and we are increasingly aware that this needs to be addressed. Then there's micrometeorites and debris. So debris is stuff that is just floating around. It could be us that left something there, or it could be something from a meteorite or piece of a planet, basically that got chipped off in an impact and got sent out on a trajectory. For that, you can select particular materials to resist impact. Design redundancy, put sensors on your spacecraft to see if this happened. And the last item, get the fuck out. This is specifically if you're in, for instance, the International Space Station. If something comes towards the International Space Station, they actually move the entire International Space Station out of the way. Preferably, if it's another satellite, they move the satellite. But sometimes they can't. And then they have to move. And with commercial spacecraft, that also happens. If you can see that something is coming and you are able to move, you get out of the way. On to the CubeSat part, the specific CubeSat part. So CubeSat started off as a way to make satellites smaller and cheaper and more available. I have a few on this slide. Some of the older ones, Cal Poly CP1, the University of Illinois had one. Then I started to become involved with Delphi C3. That's the university satellite that I worked on in Delft. FunCube1 is another one that I spend a lot of time on. And these other two, Simba and Perseus M, are two of the satellites that my company built in the early days. What's a CubeSat? That's basically also what's this CubeSat stuff anyhow, the title of the talk. So what is this about? When we initially wanted to launch these small satellites, we needed to come up with a standard to make sure that you can talk to launch providers and say, I want to launch this thing, and this is the dimensions. So they started making what they call the CubeSat design specification. It's a 10-centimeter cube with a mass of up to 1.33 kilos, and that's a unit. They call that a unit. And it usually contains off-the-shelf components, just stuff you can buy, nothing special. There is actually a ISO standardization for what they classify these sizes as, and that's called a picosatellite. So a CubeSat is a form of a picosatellite. You see both used. But if you then start stacking U's together, because you can make them bigger, they might actually leave that space. Form follows function in this case, so we really say, what do we want to do with it and how much space do we need? It's not like we have this much space and what can we put in it. So you start with a 1U, typically used for educational purposes, and then you move up to through the sizes. 2U, there's also a 1.5U because historically we've been launching 3Us as well, and if you want 2 missions in the spot for a 3U, you can make 2 1.5Us, but that's very rare. 2U, 3U is what I built at the university, so that's 10 by 10 by 30 centimeters. And for the Dutch people, they call it a melkpak, but then it would be a 3-liter milk carton, which is a bit weird. But that's, some journalists came up with that, and so they call them milk carton satellites. Then there's 6 units, which is basically 3 units stacked and then 2 side by side. Typically used for RF missions, so missions where you do some radio stuff because you need to fit antennas on it. So you need a bit more space. 8U, don't ask. 12U is Earth observation. If you need to fit a telescope, you need to fit lenses. So again, a bit bigger. And then the 16U, this is deliberately wrong in terms of formatting because it's where the instrument doesn't fit in the satellite. So you basically go up, oh, we wanted a 12U, but we actually ran out of space. Can we have a 16U? And people keep doing this. Then you start selling 60Us, and they're like, yeah, we ran out of space. Can you make an 18U? And at some point, we are wondering, where does this end? Yes, we are still nerds. So the Borg cube is also a CubeSat. It's a 2 times 10 to the power of 9 unit CubeSat, or 27. Yeah, 27 by 10 to the power of 9 unit CubeSat. And we also had an April Fool's joke where we had these Tetris-shaped CubeSats, which conform to the CubeSat design specification, with the exception that if you want somebody to launch those, you're going to pay for the volume that is left open around it. So what did we want to change with these CubeSats? Traditional space missions are entirely custom. So everything is built purposely for that mission. So you start with the mission specifications, which you also do for CubeSats, but and then they start building custom hardware. Thus even the size is custom. Or you buy the entire rocket with the satellite on it, and that's lots of paperwork. It's costly in terms of test campaigns because everything needs to be tested according to the specifications that are set by the rocket manufacturer. And everything is driven by mission requirements and is often quite slow in innovation. So we wanted to change that, and what makes it easier for somebody in a rocket to allow you to bolt something to this rocket, if you tell them, we're going to put a box on the rocket, the box is a fixed size, we qualify the box and it stays closed. If the insides turn to dust on the launch, you don't care as rocket provider because we won't open the box. So everything is sealed in a specific container. And my colleagues, if you're watching, by the way, on the live stream, or if any of them are here, I always call it a box with just a jack-in-a-box spring in it. People spend years designing these boxes, so I make myself very popular by saying that. But yeah, it is actually just a container. And these containers, they they have an inside specification, which is the CubeSat specification, and I brought one. I'm going to hold it up, and for the people on the stream, there's also a picture of it. And these are bolted to the rocket. I'm going to not speak for a bit. So yeah, I'm going to hold this up. Then you can see that this is filled with plates with springs that can move out and eject the satellite into space. So if we have these satellites in there and you close the lid, from a rocket provider it's just a box, which makes it easy to launch. Obviously there's a lot of paperwork stuck to this box, but it should be easier. I think my voice is going a bit. Let me just quickly mute. I hope the solution was Mate Cola. We'll see. So yeah, traditionally you do everything by the book, standardized, on lessons learned. There's minimal risk approach because what you're building is very expensive. And because it's very expensive, you want to have less risk. And because of that, it becomes more expensive, etc. And then it snowballs into a really big project. It's usually one-off, so you design it to be a solution for one problem only. High investment cost, long duration missions, and there is a lot of space-grade hardware, which is expensive. And then new space does away with a lot of these complexities and goes much faster. Building blocks are standardized. Hopefully with relatively low cost, and reuse as much as possible. Then you start stacking boards together. So you basically build modules and you start stacking them on top of each other in the frame. This is a 1U frame, that's a 3U frame with all the electronics in it. You start by building a breadboard. I can see some people in the audience that are working on these things. Yes, I'm looking at you, Martin. But these are flat sets, so you're stacking these boards together, and we call it a flat set because it's not a three-dimensional thing, but it's flat. Well, sometimes there's towers, but everything is easy to access. This is basically the breadboard stage. You start testing a lot of things, and then at some point you stack these up into modules, and those modules then get added together as a satellite. There's a load of stuff on the bench where you do a lot of testing, but this is your typical lab setup. So when everybody is developing, it looks like a normal, regular lab. The exception is that sometimes they go for what they call proto-flight, which is basically, if it works, we're going to launch it. So that might go to space. Because, yeah, if it works and you want to be quick, then, yeah, launch the prototype. Problem, you launch the prototype. What you're going to do if it didn't work? And then you need to figure out, okay, this thing is now in space, and I don't have anything anymore because I just launched it. And for this satellite comes in, and that's why I'm holding something that I say is not a model, but we call it an engineering model because it's an actual functional satellite. If I flip the switches here, it will turn on and start transmitting, which will make radio operations very pissed. So, not going to do that. So yeah, from the diagram to reality, you start with this rough stack-up layer design. You end up with a CAD design where you do all the mechanical stuff, and then you start building up the real thing. And then the fun starts, because CubeSat is a standard, but it's a standard to be broken. So the first 6-unit CubeSat wasn't a 6-unit CubeSat. Because again, they ran out of space and were like, can we have 10 millimeters extra on one of the sides? Please, thank you. Then Planet Labs a US startup at that time. They designed these Dove satellites. They're 30 centimeters plus 1 inch. Yes. And then there's the Naive 1 spacecraft, which has a couple of protrusions past the envelope that is normal. And then they went, can we launch it? We could, but yeah, it's not compliant. So is that a problem? And should the standards be updated? No, we don't think so. The easiest requirement that's usually broken is the form factor. And it's not a problem if you design it and then you tell somebody, you're like, hey, it's a bit bigger. But you would not believe how many people show up and they said, okay, let's do a fit check. And they're just like, oh, it doesn't fit. Did you ever measure that? No, we just designed it and CNC'd it and then it's done. One of the CubeSats turned out to be not quite a cube, which was also interesting. So yeah, surprisingly, there's a lot of failure rates. Sometimes CubeSats are not even launched on these deployers straight into space, but they go onto another spacecraft. So here's the Hera spacecraft by ESA, and in here you see 2 lids circled in red, and if you're keen-eyed, those are those lids. So there's CubeSats in this spacecraft. So we're launching a spacecraft. This is going to an asteroid. And then when it's there, it's going to launch 2 CubeSats around the asteroid from the mother ship. So these are what we call deep space deployers. And they have to sit there with a CubeSat inside all the time that they're traveling to this asteroid. So for years, they're passive. And yeah, then we deploy those satellites when we're there. So it's sort of a carrier system. And then it becomes, at some point, also kind of an economy of scale thing. We can launch these things, we can build them quickly, so here's a whole load of these deployers with a whole stack of CubeSats going in. These are those Doves that I talked about earlier, and they would literally design them with a frame around it so you can stack them in the clean room like that. So the Coke seemed to do the trick. So mission types, yeah. So there's a couple of different types of missions. This is the fun bit, but I also have to go through this quite quickly because there is quite a lot of different mission types. For instance, ship tracking, finding where ships are. Space research, telecoms, education and training, so build a CubeSat to sort of learn how to build satellites. Earth sciences and Earth observation, microgravity, pipeline monitoring, signal intelligence, looking at radio signals from space, not only coming from space, but from the Earth. Climate monitoring, technology, there's all kinds of things. I'm gonna have to skip through quite a few slides because of the... Yeah, okay, so this is, one of them is that's my hobby satellite, that's the one that's standing over there. A FunCube, and we now have a whole fleet of these things. This is basically one of those educational types of missions, where we build a satellite that can be used by radio amateurs to just have conversations, but also schools can pick up the signals in the classroom and actually listen to the signals and looking at them. And then there's a short video of what the signals sound like. If that is, yes. Nou, dat is de telemetrie, dus dit is de data. Dus hij zendt nu gewoon allerlei gegevens uit, batterijspanning, et cetera. So there's data in this. Het werken nog niet goed weet waar die zit, dus we kunnen nu gaan kijken de transponder. Dus daar kunnen mensen via praten. Dus dan gaan we naar 69. Kijk, hallo. Yeah. So there's actually people having a chat.
Echo radio, Delta Golf 0, Echo radio.
Yeah, hardware, I'm going through that quite quickly. One of the other missions, Earth observation. The AMS satellite is for agricultural monitoring. That's where AMS stands for, agricultural monitoring satellite. So, for instance, you can look remotely at a plot of land and see how the crops are doing. A lot of farmers that have really big farms are actually interested in this kind of data, but also agencies that want to see how productive a certain area is, or if there's a problem that is in a wider area. Enabling communications in remote areas. That's mostly for Starlink and Project Kuiper and other companies that already did that, like Iridium and Inmarsat. CubeSats, not so much. Then some radio astronomy. This is a while ago. This was a cooperation with China. They were launching a relay satellite, and we were allowed to put a payload on there that did radio astronomy. If you want to listen to old radio signals coming from space and figure out the history of the universe, you need to go back quite a long time. And because frequency shifts occur when stuff moves, Doppler shift, that's called, some of the oldest radio signals that are still around have shifted to low frequencies. Problem is, we are all using these frequencies right here, so the Earth is extremely noisy, so you want to get away from that. So what we do is we go behind the moon and use the moon as a shield, so that the signals that we generate on Earth do not interfere with the measurements. So you need to be basically behind the moon to do this kind of science. What is cool is this is a traditional space mission, a really big satellite, but we chose to go with internals that are CubeSat. So the box that gets bolted on the satellite is based on whatever they need, but the insides are basically a CubeSat that just doesn't get deployed into space separately, but bolted on another spacecraft. And then you do the same whole process, but then with a bit more traditional space. Then we come back to some of these more CubeSat-oriented hobby. Well, it's not hobby, but antenna tests, for instance, we use helium balloons to keep the antennas up, because gravity would mess that up. And then after a while, you get the word that it gets launched in China. And you get a picture back that basically shows the moon, Earth in the background, the antenna that you built in Delft, and the mother spacecraft, which is really cool. And then you want the data, but this was a military mission on the Chinese space program, so you don't get digital data transfers. You get everything printed out in hex, on paper. Right, some Earth observations. I'll skip straight to the nice, shiny images that we can do. So these are coming from CubeSats. This is a typical image from a 6U CubeSat in this case. And if you zoom in, you can see quite a lot of these things. South Africa with different wavelengths, images of cities. This is, for instance, San Diego, San Francisco. I see the contrast is quite low. San Francisco and Jeddah. Again, they're not Google Maps zoom in all the way, but these are coming from a satellite of which 2 fit in this box. And then landscape, so there's a lot of interest in coastlines, agricultural areas, etc. I want to get to the last one, climate monitoring. We're building a global warming methane monitoring mission. Greenhouse gases cause global warming. I think we all recognize that. So we want to actually image the Earth with 2 satellites flying in tandem and figure out where are these emissions coming from. For instance, there's a leak in a methane processing facility, and the owner doesn't care. They just let the methane go. Now we can actually see that and say, hey, you're leaking a load of methane. What are you doing? Why are you doing that? There's already an instrument that did this in a bigger satellite, but we needed to fit in, so a lot of complicated engineering was done to actually make all the mirrors fit into a really tiny space. So this is a 12 unit, I think it's a 12 unit, that has a greenhouse monitoring payload in it and does all the emission monitoring, and there's 2 of these. And we're building them currently for ESA. I will skip this. Some maritime tracking, so tracking ships from space. All ships are fitted with a small transmitter that basically says where they are. But as soon as you're off the coast, they disappear because there's no monitoring stations anymore. So if you go in space, you can see all these ships. But the problem is they're all transmit at the same time because they don't know that there's another ship way outside of their range that's being picked up by the same satellite. So you need to deduplicate all these messages because they're transmitting 2 ships at the same time. Normally the transmitter checks, is the channel clear, starts transmitting, but yeah, if they check, they will only have the range of whatever the ship has as range. And then if there's one here and one there, they don't know that they're transmitting at the same time. So from space, that's quite interesting. And it was never designed to do that. This is the final slide, or one of the final slides. I have one more video and a nice slide. So this is a reminder that space is still hard. Stuff still explodes. And very, very occasionally, your stuff makes it back to Earth. This came out of the explosion. I can't tell you what launch that was on, but this fell from a couple of kilometers down, landed on Earth, was delivered to us years later, saying like, oh, we found this thing that you lost a few years ago. And then when my colleagues inspected it, they opened one of the doors, saw all kinds of spider webs and deformation and whatever, but one of the doors did not open until we actually tried it, gave a deployment pulse, and it worked.
It's done.
Sweet.
And there was still a dummy satellite in that door that survived the fall from a few kilometers down. That was it. Thank you for your attention. I don't know.
Yes.
Do we have time for questions?
We have time for questions. So there's a microphone here in the hallway. You can use that. So please move to the microphone so you can ask your questions. I already see someone moving. Please stay a bit quiet during the Q&A because people can actually hear this on the stream. First question.
You showed us that these...
Can we hear the microphone a bit louder here, please?
You showed... Yeah. Sorry. You showed us that these units at some point eject... the spring ejects a CubeSat.
Yep.
The spring also pushes on the satellite. Does it change course?
Yeah, so there's actually a lot of complex mechanics. So the springs push on a pusher plate that pushes the satellite out, but the satellite itself actually has feet with switches in them with also springs. So those actually push the satellite even away from the plate, and these are the activation switches that turn it on when it's gone out of the pod. So there's a lot of complex mechanics, and a lot of people are also investigating what happens if one of the switches gets stuck, whether it flips out or not, that's all been designed very properly to always work.
Thank you. Anything from the signal angels? No, nothing. Then we go to the next question.
In the way that many things are, with some which do ruining it for everybody,
we are now contending with the problem of Starlink precipitation. And as more and more stuff burns up in the upper atmosphere, is there likely to be changes in the way the rules are about just burn it up on re-entry as the end of life for satellites? And is that going to thus make it very difficult for CubeSats, which don't have maneuvering and all of that, so they can't just be put into a parking orbit and stuff like that?
Yes, that's a very good question, and the answer is yes, it will get harder. There's a lot of regulations already being made for this. A lot of launch agencies actually require you to analyze how long you're going to stay up and limit the amount of time that you will stay up in orbit to whatever the mission requests, with a bit of margin. So if you have a satellite that can only operate for 1 year, don't go somewhere where it stays for 20 years. That's dumb.
The materials that you can use?
They do, but that's also based on analysis. So it's not particularly a list of things to avoid. It's mostly, does it burn up fully? Or is there a risk of landing back on Earth? If you have a big chunk of titanium that doesn't burn up, maybe don't do that.
Thank you, Val.
Yep.
Okay, next question, please. Very fast one, if possible.
Yes,
Short answer.
About space debris, is it possible to use any passive radar for monitoring debris on your own satellite?
Sorry, the passive radar on the satellite, yes, or on the ground?
On your own satellite to detect nearby space.
Yes, that is absolutely possible. We also have passive radars for Earth observation. I don't think they actively use it right now to detect proximity in space. I'm not aware of anything, but...
Thanks. Final question.
Hi, if as an amateur, say a Y conference visitor, you would want to get your hands on a satellite to work on it, what would be the best approach?
Find a team that is already doing this in a university or another affiliated team, because there's plenty of people building these already. And they really welcome enthusiasts that are not yet in education, but are a bit more experienced in other fields. So hacking is definitely, the hands-on experience is something that's often lacking.
Thanks.
So yeah, universities.
I'll refer you to after the talk. So
sorry, Matt.
Within the time and within the recording, give a big applause to Wouter.
Thank you.